So let's see how one goes about solving this problem. Okay. So in a simple way, if I go back to this slide, I I'm going to assume that, okay, first of all, I have the Hamiltonian. So if I take the derivative of this with respect to u and set it equal to 0 in order to maximize this, or that's one way to do it, but it's sometimes derivative may not give you the maximum because it may give you many other values, and but we have to pick up the maximum. So suppose we are able to pick up the global maximum of this Hamiltonian with respect to u, then that global maximum I'm going to call u star t. Well, the u star t will be a function of x star, lambda, and t, right? Because after all, there's x star here, there's a lambda t here, and there's a t here. So those are the three quantities. So the u will be implicitly a function of these three quantities. So u star t in general will be this function. If I put that function in here and in here, then I have two equations. One is an x star dot, one is lambda dot, and I have no u anymore. Everything is x and lambda. So I have two differential equations with u already out of the picture, and I can, in principle, I can solve this equation. How do I solve this equation? Well, there are many ways to solve the equation, but in numerically, if you think about it, what are we going to do? Think about, I begin with this initial condition because this I know that condition. And I'm going to make a guess of lambda 0. So call it lambda 0. So I have x0 and lambda 0, and I have both initial condition. And with the initial condition, it is just a two-dimensional differential equation. I can solve it. That means with x0 lambda 0, I solve to the next level, and one way to do is to do it in the increment of delta. So I can go from 0 to delta, delta to 2 delta, 2 delta, 3 delta, and I keep going. And if I keep delta small, I numerically solve the problem, and there may be analytical way of solving the problem. But when I do with lambda 0, I will come with some lambda t. That lambda t may not satisfy this because I know what it is. Because I will know what x star t is, I can put that in there, and that may not satisfy. If that doesn't satisfy, I change the guess. I will keep changing the guess until that lambda 0 is the right value of lambda 0 that satisfies this. So in solving a two-point boundary value problem, you might include a guess, and then the guess has to be proper in order for you to be able to solve the problem. So there must be some way of guessing those things. So that's where we will come to this Excel, and we will see that in Excel, they can do a very fast back and forth and will give you the value of lambda 0 right away. And once you have the right lambda 0, you have this problem solved, and you have this value solved for every t, and you have an optimal solution for the problem. So that's the idea. The idea is to change the original problem in functional space to a problem at each t in terms of x and lambda, and then try by doing that, solve for x, lambda, and u. So you're solving a set of differential equations, and you're solving an optimization problem at each instant t. And by doing that, you're building the solution for the original problem that's given to us, which is far too complicated to solve. Okay. I'll make a little bit more remark there later. So let's get the objective function. Let us see what is the meaning of all of this. This is, by the way, you will not find in engineering books. This interpretation is, I should put that on YouTube somewhere, because this is a pretty nicely done interpretation in detail that allows you to see what is going on. You can find them in some economics books, but not at this detail. Okay, so here's our objective function. We can think of F as the instantaneous profit measured in dollars per unit time, and S is the salvage value in dollars system at time t when the terminal state is X. So this is when the terminal state is X, and when the terminal, whatever xt would be, we will have the salvage value for that xt. Multiplying 2.18, whatever it is, multiplying 2.18 formally, which is the definition of Hamiltonian, I get h dt is f dt plus lambda f dt. But this is f dt and f is x dot, so I can call it lambda x dot dt. But x dot dt can be written as dx, because this dx dt 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 cancel out, so I get this. So what does that mean? That says that Hamiltonian consists of two contributions. One is the direct contribution to the objective function from t to plus delta t, t to t plus dt. And the second is that if when I use this u, I will change the state x to x plus dx. So because I get the immediate benefit, which is given by the first term, but I also change my state from x to x plus dx. So I should have the value of dx factored in. But the value of dx is just lambda times dx. So if I can take the value contributed by this u in two ways. One is to give me the profit, and the other one is to change my state to dx, which may give me future profit, additional future profit. But the additional future profit it will give me is exactly lambda times dx for small dx. Okay, so if I can take the current profit and the future profit, and you can maximize that at each point in time, then hopefully it maximizes the objective function. So that's what's going on. So I maximize the total contribution to j from t to t plus dt when x equal to x and ut is u in this interval. So the maximizing h means maximizing this total contribution from the earnings that comes from capital F and the value of the additional state. Now, there's a lot going on in the stock market these days. I'm not talking about Reddit right now, but think about when you invest in a company, you have a share of stock. Now, the share of stock, if you have a time t and you hold it for 1 day or time dt, then what happens in that 1 day? Well, in 1 day, you might get a dividend, right? Because companies give dividend, and in that 1 period, you get a dividend, so that's your dividend, FDT. By the end of the 1 day, the share that you have, whose price is P, you got some dividend on that price, but the price has gone up in 1 day, gone up or gone down. So that price is your capital gain. So this is the capital gain. So this is the dividend, this is the capital gain, if you think in accounting terms, okay? And so you're maximizing the dividend and the capital gain, the sum of those two. Okay, so this is the interpretation of the Hamiltonian. Well, let's see, what is the interpretation of lambda dot? Well, the lambda dot is the change in the price of the share. Or in the company setting, it is the change in the value of the state. So lambda dot can be written this way, and its value is this way. The first equation I can write as minus d lambda is hx dt, and hx dt can be written as fx dt and lambda fx dt. So what is minus d lambda? Well, if I hold the capital, its value is lambda right now. If I hold it for a dt period, its value will be lambda plus d lambda. Okay, so the cost will be minus d lambda, holding the capital. That means if the share goes up by, let's say, 10 cents, then the cost of holding the share is minus 10 cents because you're getting a gain. If the share goes down, the cost is plus 10 cents. Okay, so the cost is minus d lambda. That is the marginal cost of holding the capital. What is the marginal benefit of holding the capital? Well, you earn money by you get some dividend. Or if it's a inventory, then you create some sales and that give you a profit. So the marginal revenue of keeping that capital for one period is the direct marginal contribution, which is fx dt, and the indirect marginal contribution, that is this. So that is the total marginal contribution, and that is the total marginal cost. So this gives you marginal cost equal to marginal revenue. So this lambda, which does that magic for you, does it because of it satisfies a famous economic principle, which is the first order condition of optimization. If you have a revenue function and a cost function, the profit is revenue minus cost. And the first derivative of the profit says marginal revenue, which is the first derivative of revenue, equal to marginal cost, which is the first derivative of the marginal cost. So that is the value of lambda. Look at another way. I can integrate this guy. If I integrate this guy, I get lambda t. I integrate from actually t to small t, big T. Then I get lambda t plus t to t plus whatever that. This one is nothing but Sx, and this is the integral of that. You can see what's going on here. The price lambda t of a unit of capital at time t is the sum of its terminal value lambda t plus the integral of marginal surrogate profit rate from t to t. If you think about finance, lambda t is the price of share, and lambda t is the price when you sell the share at capital T. And so the value of the price of share right now is the value you get at capital T and all the dividend you get from T to T. Now, Sunkai asked about the discounting rate. When I talk about the discount rate, this will be the discounted present value of the dividend, okay? But right now there's a T here, so that takes care of that discounting. So we don't talk about discounting right now because it's more general setting than discounting. So lambda t is a unit of capital T, is its marginal salvage value. In a special case when S is 0, we have lambda t equal to 0. So clearly no salvage value. As clearly no value can be derived or lost from an infinite increase in xt because lambda t will be 0. So it doesn't matter where you end up. Okay. So this is another way to express lambda. Let's look at some examples now. This is about the simplest example. So what I'm going to do now is to apply this maximum principle to very simple problems. And it gives us some confidence that we can solve this problem using maximum principle. It gives you the idea behind the maximum principle. However, problems are going to be a lot more complicated in general, and solutions will be not so easy to come by because maybe you need computations, maybe you need another level of math to solve these problems. So that's that. So let's start with a very simple problem. Maximize minus x dt, x dot equal to u, x0 equal to 1. Let's assume, let's specify the control to be minus 1 to plus 1. So if you look at our problem 2.4, which is the general control problem of this chapter, then capital T is 1. F is minus x, S is 0. So it's a Lagrange form, not a Boltzmann form because the S is not there. And F equal to U, which is this F. And because F is minus x, x dt is the area under the trajectory x. And minus x is the negative of the area. So we are actually maximizing. We are 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 actually maximizing the negative of the area under the curve. So we are minimizing the signed area. Okay, because x can be positive or negative. So the area has to be, the integral has to be of the signed area. So there's a curve and it has an area under the curve, and we are trying to minimize that area, okay, or maximize the negative of that area. You'll see the picture later. So we form the Hamiltonian. It's minus x plus lambda u. And to maximize the Hamiltonian at each point in time, it is clear that u star t is 1, which is the value 1 coming from this one here, this one here. And it is minus 1 if lambda t is less than 0. But it can be any value between minus 1 plus 1 when lambda t is 0, because when lambda is 0, you maximize the Hamiltonian, u could be anywhere between minus 1 and plus 1. So we can keep it arbitrary for the time being, and we can set it up. When we see the problem, we can decide what we want to do here. Okay. This, in chapter 1, we call bang-bang control. Okay. So we define this function, which is like this, is this one. U star t is bang of minus 1, plus 1, and lambda t. So it takes minus 1 value when this argument lambda t is less than 0. It takes the plus 1 value if this is bigger than 0. And it takes any value between this when this is equal to 0. Okay. So that's the form of the optimal control. So I can substitute, because my beginning value is 1. So I substitute the control. And when I substitute the control, I get x dot t is 1 minus t for t between 0 and 1. And the area of the integral is negative area is minus half. So here we get the integral. See, this is the trajectory from 1 to 0. And this is the lambda t, that is minus 1 to, the lambda t goes from minus 1 to 0. And because it's minus 1 at the beginning, the control is minus 1, because bank function tells you the control is minus 1. But lambda t is negative everywhere. See, lambda t is negative everywhere, except lambda t is negative everywhere except at t equal to 1 when it is 0. So you can see that I can put any control I want on that one point. Doesn't really matter what it is because we have finished. So we can set it at exactly minus 1 here as well. So the control is minus 1 all the way, and I have an optimal trajectory, and its value is the area of that triangle, the negative of the area of that triangle. Now, this is in a second edition, doesn't have these kind of things. So I did a lot of things about interpreting these. So now I'm going to do one more thing. I'm going to start with a new value 1 plus epsilon. So I'm going to perturb the value 1 by 1 plus epsilon. Okay. If you look at geometrically, you can see that the control in this case is going to be the same. We will go there. We will see numerically later. We'll go to the equation later. So the new trajectory will be given by this dotted line, and it will stop at this epsilon. Okay. You can sort of see that the new trajectory as an area. Well, first of all, that area starting from there all the way up to here is still half. And this area of the rectangle down below is exactly epsilon times 1. So the area, the total area under this curve is half plus epsilon. Okay. Now so we have the objective function, we have the optimal control. Now let's look at the math here. So J star is minus half. And if I change this to my small epsilon, then the initial condition, so I now have a notation where this means the initial condition for this objective function is 1 plus epsilon. Then by our value of lambda 0 to be minus 1, I can see that the new value should be approximately minus half plus lambda 0 times epsilon plus some little o epsilon. So I can see the value to be minus half minus epsilon little o epsilon. That goes to 0 as epsilon goes to 0. But in our case, it was minus half minus epsilon. So in fact, that is exactly 0 in this case. So you can see that this value of lambda 0 works for us. Exactly. We have a meaning of lambda 0 exactly by this meaning here. We were able to estimate the new value of the optimal control. And the new trajectory is this, because obviously u star is minus 1. And so this control remains optimal, and the new trajectory is 1 plus epsilon minus t, which is given by the dotted line. I write this as x star or yt, where y is the initial condition. So this new trajectory is given by this, and its value is minus half epsilon 0, so everything works. Here, it will work also for minus epsilon if you go below, but sometimes you may have to do different calculations for positive changes and negative changes. You may have to do different calculations, but it doesn't matter. The mathematics goes through. Okay, let's look at another example. Now I change it to 2. And I have the same problem. What happens now is the following. This is very important. I'm now here. Forget that one. We are still original problem. And now I'm here. But once I'm here, the control, if I put +1 control, it goes up again. The area increases, and that's not good. If I go down below, again, the area increases because the signed area. So the optimal solution is to just stay at 0. Okay? And lambda 0 stays at 0. So let me give you the solution first, and then I will talk a little bit more about what's going on here. So lambda dot is 1, lambda 2 is 0, t equal to 2, and then lambda t is t minus 2. So we go a picture. So this is lambda t going minus 2 to 0. The trajectory is going from here to here. Oh, I'm sorry. What I gave is the next problem. Okay, this is, sorry. So we have the solution here. We have a solution here. This is minus 1. So the area is 0 now because it's a signed area. So this is plus area. This is minus area. And sum of these two areas is 0. So the objective function value is 0. So this is again a problem. The third problem is more interesting. I have minus half square x dt. And now what is happening is that even if an x is negative, x squared is positive. So it's no longer the signed area. We are actually trying to minimize the area under this curve half of x squared. Okay, it's the absolute area, not signed area anymore. Okay, so let's solve this problem. Hamiltonian is half x squared lambda u. I want to maximize this Hamiltonian with respect to u. Okay, so u star lambda is again bang bang. Okay, because lambda u is linear in u. And it's bang bang. So now I have to solve adjoint equation. Well, the adjoint equation is x now. And lambda 1 is 0. I cannot solve this equation right away because it's coupled with x dot equation. But I can do a guesswork. So what I'm going to do is I'm going to assume that the control, you're going to look at some key from the picture. I'm going to assume that I'm here and the area I'm going to reduce from 1 to lower value in order to minimize this area. So I can use control -1 That will give me the trajectory x star 1 minus t. Once I have the trajectory x star 1 minus t, I can put that value x as 1 minus t. So I have a lambda dot 1 minus t. I solve lambda. Lambda dot is 1 minus t. Xt is 1 minus t. And the lambda dot 1 minus t, I can take integrate, I get this value. Okay? And then when I get this value, I can see that this value is negative all the way. So my initial guess of control minus 1 is correct. If it's not correct, I have to redo it. So this was a correct guess. And because of the correct guess, I was able to solve the 2-point boundary value problem, which was boundary value problem in x dot and lambda dot. It was not possible to solve lambda directly without knowing x, like in the previous example. But I did some guesswork, and I did the solution, and the solution satisfies the maximum principle. So we are good. Now I take the problem and change the integral to 2. And now you can see what happens if I take the integral to 2. It's good for me to keep the lambda at 0 and a control at 0, because if I go this way, I will increase the area because it's the absolute value. If I go this way, I'll also increase the area because the absolute value of the area is still positive. So no matter what I do here, I will increase the area or increase the, since I'm going to increase the negative objective function, but the positive objective function will decrease because I always solve the maximum with the minus here. So what I'm trying to say is that I will not be optimal if I go this way or go this way. So the best thing to do is stay at 0. Okay? So let's see what is going on here. Notice that when I define the bank function, this is arbitrary. But it cannot be arbitrary if I have a trajectory. It can be arbitrary at one point, and I can do anything I want at one point because that does not add anything to anything. But if it is more than one point, I need to find its value. So what I'm trying to say is that bang function gets its value by optimizing, because what happens is if so lambda t is 0. So let's see what's going on here. Bang says at any point here, because lambda is 0, I can go up or down by using control 1 or minus 1 or half or 3/4 or whatever. But as soon as I do it, I'm going to go above and my area will increase. And as soon as I go above, any point above, the control is minus 1, so I come back again down here. So what happens is I will go up and down again. I'll go up and down again. I'll go up and down again. And if you take this epsilon, or not epsilon, but delta, go like this, and if you go up a little bit, I have to go back again. If you go even further a little bit, I go again. So in the limit, I would stay here. So in the limit, lambda will be 0. Lambda will be 0. And when lambda will be 0, the lambda dot is also going to be 0. And so lambda dot will be 0, so the lambda will stay at 0. This is called a singular control. This is pretty important. Later on, we will see how the singular control comes into play. Singular control is also fairly sophisticated in some way. And what I'm trying to say is that even though bank function doesn't define thing at any given point, the optimal control figures out how to get the value. Okay, so the value is such so that the bank control can be maintained at bang, and that is called a singular control. If I come to a point where the control is arbitrary, and if there's a way to maintain that arbitrariness by finding a control that will maintain that, then that control becomes bang optimal control. Okay, and that there's a whole course that can be devoted to bang control, Well, we will only just go like this, and then we will, in application chapter, we will see number of bang control examples, and we will see the value of those examples in economic setting. They are very important in terms of solving some of the economics problems. So that's all I can say right now. I will go very fast on this one. So now what I want to do is I want to change to the value of x0 to 1 plus epsilon. And remember now that the value of the objective function at the optimal solution is exactly minus half times 1 minus t squared, because xt is 1 minus t. Okay, and I take the integral of that. Integral comes to be minus 1/6. So that's the value of the objective function. And if I take x0 to be 1 plus epsilon, then the lambda 0 times epsilon plus epsilon 0 O epsilon is minus epsilon 2 divided by plus O epsilon. So we want new, so our new objective function will be minus 1/6 minus epsilon divided by 2. That is the approximate value of the new function, right? This is what the marginal value lambda means to us at any point. At any point means at 0 is just any point. So you can also try it at another t. You can try it at another t along this path. For example, you can try it at this t and change the value here by epsilon, and you can do the same calculation, similar calculation at that point. So the calculations are parallel and similar, and you can perform them at any point in time if you want to do that. So now we have this. So what happens? Well, the control directly, we obtain a new control. The new control is minus 1 up to 0, 1 plus epsilon, and then it is 0. Because now when I do that, I have to go. So here's what happens. So when I go from here, I will get to 0 at 1 plus epsilon, time 1 plus epsilon, not at 1. And so I get 0, and then from here I use the control 0. So I have a little bit here, that area, so I have to compute the area in a way. So when I do that, I have this control. When I have this control, I have this trajectory, which is easy to do. So I have this trajectory. And now I can do once I have the trajectory, I can do the objective function. And you can see the objective function is exactly this. But as epsilon goes to 0, these guys will go to 0. These two guys will go to 0. So I'm left with this, exactly this form. And this form is exactly what our value of lambda told us, is minus 1/6 minus this plus 0 epsilon. Exactly like this. Because lambda 0 is minus 1, so it's minus epsilon. Sorry. So it's minus epsilon plus O epsilon, minus 1/6 minus epsilon O epsilon. Okay. Carry out the detail only in the case of, there's one more thing we're going to do. We want to find out the VXT. Okay. I want to find VXT. We can actually take the derivative of that with respect to x and also find lambda. So given that, let's see what the value function is. Now, the value function, at different point will be different in different cases. So I'm going to take the value function only for 0x less than 2 minus t. And leave the listing of the other cases and required calculation is exercise 2.13. So let's just do this part. This requires some work. I don't know if there's a picture there somewhere. There's no picture. So this is a problem which is better with a board, but I think we're going to just do it without that, and you're going to have to think through a little bit when you want to details of this at home. So I take 0 less than x less than 2 minus t. because if I take differently, the endpoints may be different. So that's why I can only do this right now. So this is the initial value at t. So let's take the initial value x at t, and s is the now new time, which goes from t on. So what I'm trying to find out the value of being at time t with the state x. So the optimal control is -1 from t to t plus x, and 0 from s to tx plus 2. You will, when you draw the picture, you can see that this is just like I did the picture earlier. When I did the picture earlier, I started from here, then I went up to there, and then I went like this. But now if I start from here and go like this, then it will go like this, and then go like this. And so you need to make sure that you take the value of x, which are not here or not different places where might not be I mean you can do it everywhere, but it will require you to figure out exactly what's going on with the trajectory from different values of x. So once I have this, I can solve the differential equation, and the differential equation gives me this value. Okay. Then I can compute, since I have a u and x, I have x, and I can compute the value of objective function, which is j star 1, so I can have 0 to 1 plus epsilon. I can compute all of that, and this gives me this value. And, oh, I have to go further. So now I can put that value in the objective function, which is right here. I take the control from t to t plus x, which is the value here, because after that is 0. So the only value that you get from vxt is up to t plus x, and then goes to 0. And you take the integral of this, you get this. So you can integrate it if you want, but in order to take the derivative, we don't have to integrate. So we take the derivative inside the integral, and we substitute the value x star t, and we can find out the v sub x star t is this value. And that's what we got as the objective function earlier with x equal to 0. And when x0 was 1, we got at 0. If this was 0 and this was 1, we got this value. Okay, so there's a way to control, and so any question? So you see this is minus half. Lambda 0 was minus half. If you take the derivative of this, if you set this to be 1 and this to be 0, you put the 0 here, you get the value minus half. So you can see that the lambda 0 is exactly the marginal value v sub x. But now I have marginal value at any other given time t. So if I give you an increment at this point somewhere, if I have a value here, I got the value vxt, and if I take epsilon here, I can tell you exactly the value of that extra epsilon at this point in time by simply multiplying that epsilon with this value. So you can see that lambda t actually gives you the marginal value of epsilon at any given time t, when there's at any time t when the value is x. Okay, the last example, numerical last example before we go to the sufficiency condition as well as the Excel part is this example. Now, this example is the first example so far. See, in all the previous example, so far, the optimal solution was trivial. You can look at the geometry and you can find the optimal solution, and then you can show that the maximum principle will also give you that solution. So maximum principle doesn't really help you that much in terms of giving you the solution because you guess the solution in any case. But here's the first example where maximum principle actually will give you a solution, and a guessing solution would not be easy. I would not be able to guess that optimal solution for this problem. If I give you this problem and you are trying to figure an intuition of how to solve this problem and give you an optimal solution, I'm not sure I'm able to do it. Maybe Einstein can do it, but I don't know how to do it. So let's solve using maximum principle. So Hamiltonian is given by this, and this is given by that. So optimal control then is maximizing this. So I take the derivative of that with respect to u, set it equal to 0, I get this. So I can maximize this Hamiltonian by first order condition. It's dh du equal to 0. So I get this. Once I get this, the adjoint equation is this one, which I can solve because it doesn't involve x. So I can solve this equation directly. So I have this solution. This is easy to solve. It's a first order linear equation, and I have given the solution of such equation in the appendix. You can do it directly by integrating, or you can go to the appendix and find the solution of this by integrating factor. Okay. So you use the integrating factor ET as shown in appendix 6, and you get the solution. Or you have d lambda divided by -2 minus lambda equal to this dt, and then this gives you a log. You integrate on both sides, and this gives you a log. This is just the integral of dt, and then you can easily solve that as well. Okay, so there are two ways to solve it at least. So I have lambda t. So I can put lambda t here. I find u star t. U star t now is this solution. Notice that this value may not satisfy this condition that we have here, 0, 2. So if it's below 0, I will set to 0. If it's about 2, I set to 2. If it is exactly between 0 2, I will set that value exactly there. So if that value, u star t, which comes to this, if that is between 0 and 2, I keep that value. If it is about 2, I go to 2 because I cannot go about 2. If it's below 0, I cannot go below 0, so I keep to 0. This function is exactly the SAT function that I told you in chapter 1. So that's the reason why I define this function. This function is comes from the SAT comes from the word saturated amplifier. The amplifiers are these devices that cuts off the current when the current exceeds certain amount. And so if the current exceeds this amount, it cuts off to 2. So that's why it's called the saturated amplifier. And the SAT function is function of this kind. Geometrically, that is the unconstrained control. And the SAT function chops it off here at 2 and chops it off here at 0. So the optimal control from 0 to 2 is given by this, then this, then this. You can now see that we got an optimal control using the maximum principle without guessing. And if I were to guess it, I would not know how to guess it. So I actually have solved the problem. So notice now, this is a functional optimization problem. It is very difficult to solve because the only way to solve that functional optimization problem is you take a trajectory u like that in this area. With that trajectory, you solve that equation. With that equation, you integrate that and you find its value. Then you change this trajectory to another trajectory like that. Again, you do the whole thing, you take another value. So you will take infinitely many trajectories in this interval and keep finding the value of those. So I will have infinitely many values given it's not just countably infinite, it's uncountably infinite. And so you have uncountably infinite problems with every trajectory. You have to first make sure that you have got all the possible trajectories between 0 and 2, which are like these, which are not have to be differentiable. They can be like um, piecewise continuous. They can be more complicated. And then you have to integrate them. You solve for those trajectories, this, which is going to be numerical. Then you put that one, and this is going to be numerical. Then there will be a value. You have to compare that to the previous value. And you will have countably infinite values. You have to compare one against each and find the best. That is, in principle, how you solve this problem by brute force. And that's not easy to solve. There's no way you can brute force it if you had infinite amount of time on the. You need a huge amount of time on a computer and an algorithm to do all of that. Okay, but we have it here using maximum principle. Next thing that we do is sufficiency condition. Okay. Now we show that the maximum principle is also sufficient if we have some regularity on this Hamiltonian. So let's define the Hamiltonian function, which is like this. Let's take the maximum of this vector u. This you can do for it's a regular optimization problem. So you can in principle define it, and then you call this to be derived Hamiltonian. It doesn't depend on u anymore because u will be a function of x lambda t. So you put u as a function of x lambda t, which is going to be this function u star of x lambda t, and then you get this function. I take the derivative of this function, and it is a trivial kind of argument that the derivative of this is exactly the derivative like this. So if I take the derivative of this maximized function, it is the same as the derivative of the interior function without the maximization. Okay. And this in economics is called the envelope theorem. Okay. A simple proof is this. More complicated proofs are available in books and other places. So the simple proof is like this. I take the derivative of this with respect to x. Well, derivative with respect to x is h sub x, then h sub u star and u star sub x. This is the total derivative. But remember, h sub u is 0 by first order condition. So this vanishes. So this is when u is not constrained. But if u is constrained, then it turns out that this is not 0, because at the boundary, you have a Lagrange multiplier. So this doesn't have to be 0, but then this will be 0. So you will have this 0. Or you can have a condition where this could be 0 in some direction, and that could be 0, not 0 in that direction, but this could be not 0, and that could be 0. Regardless, the product of these can be shown to be 0 in very general setting. But in this setting, when u is unconstrained, it's very easy to see. So that's all I'm going to say here. So the boundary, then for each ij, either this is 0 or this is 0 or both. Okay, so somehow this product is 0. We use these conditions to prove sufficiency condition. That's another thing, proof that we give, which is also very simple. Let u star t be the optimal control. Let x star t and lambda t are the trajectories that satisfy the maximum principle. And then u star is an optimal control if this is concave for in x for each t. And the sxt is concave in x. Kushali, are you there?
Yes, Professor.
You need a space between sxt and is.
Okay, slide 67.
Right. Thank you. By the way, participants in the course, if you see anything either a typo or something that you didn't understand and you want us to explain it better, then let us know, because we are making some additions to the third edition, which are minor additions, typo corrections, etc. No new material will be there. But if there's any improvement that we can make, which improves the explanation to some extent, then we can add that if it's not too much. Okay, so just keep an eye for this. Okay, so by definition, this is the maximized Hamiltonian. So we have this. But H0 is differentiable and concave. So we have H0 is less than that plus the tangent. That means that if it's a concave function, then the tangent approximation overestimates the function. So look at this. If I give you a concave function like this, and at any point I take the tangent, then approximation of that function is given at the tangent, where the function is below it. So this function is below the tangent approximation. Is that clear, anybody, or do I need a whiteboard? Is that clear? That this inequality, the function is overestimated by the tangent. It's more than the actual value of the function. The approximation using the tangent is more than the function value. Okay, so that's a concave. Convex is the other way around. Okay, so we have, this is the approximation, because you go from x to x star t, and you take the slope and you multiply the slope by this, that gives you the point on the tangent. Okay, clear? Everybody clear? Yeah, because I cannot see your hands. When it's clear, if it's not clear, you raise your hand. Okay, so if I don't see any raised hand, it means it's clear. Is that okay from now on? If I ask you a question, and if it's not clear, you raise a hand, because I don't want 6 hands raised for clear. I want people who are not understanding to raise hand. Okay. So now we can do envelope theorem. We know this we can replace by the H0 of the Hamiltonian, because this is the derived Hamiltonian. So we can replace that by this one. Okay, so that's the envelope theorem use. Then we have adjoint equation. So the definition of Hamiltonian gives you this, and H sub x gives you lambda dot. So we put lambda dot here. So by definition of H and adjoint equation, I can write this inequality as this inequality. But now what you can do is I can put this guy and this guy on this side, which is actually on that side. So I put this on that side. So that is bigger than equal to side. And the other things come on this side. So what comes on this side is lambda dot xt minus x dot. And this one and that one can be written as x dot minus x star dot. This is lambda t times f dot minus f star dot, or f of, or x star dot. This is x dot, this is x star dot, this is x dot. So I get this. Notice this is a full derivative. This is d lambda dt x lambda dx dt. So this is actually a full derivative. I can write this as a d of lambda. I can write this as a d of, I'm sorry. When I take the integral of this side, I get the objective function at optimal, at the trajectory, and the objective function at any other place. Okay. And I take the derivative of this side. This is a d lambda of x, and I can have, when you take from 0 to t, I will have capital T and a capital 0. Okay, so that's what I get. Okay. I think this is, let's assume that S is 0 for the time being, okay? So let's ignore this. So if you ignore this, I don't have this, okay? So on the left-hand side, suppose S is 0, so on the left-hand side, this is the objective function and optimal solution, this is the objective function, any other solution. S is 0, so this goes away. But this is lambda times that minus lambda 0 times that. So that what I meant by this. This becomes d of lambda times x minus x star. The total derivative of the product lambda times x minus x star. So it is the total derivative of the product. So the integral would be 0 to t would be lambda t times xt minus x star at capital T, and lambda 0 times x minus x would be at 0. So it will be exactly, remove s is 0, so it will be lambda t times this minus lambda 0 times this. But when s is 0, lambda t is 0. Okay. And this is 0 because x0 equal to x star 0. This is the initial condition. So when x is 0, this is 0, this is 0. And this is optimal value. This is not at any other place. This said this is better than that for any x, for any other u. So I proved that sufficiency condition of maximum principle. Now if I have s in there, then s is concave. So I can write s to be this way. And all of these can be added to this function without, when s was 0, now we have to add this guy to this. So this becomes the objective function. We add this guy to this. So this becomes the objective function with s. And this lambda t now, this becomes lambda t. So this becomes that. And that then cancels out and becomes 0. This becomes 0. This is not 0, but the product is 0. And this is not 0, but this becomes 0. So the product is 0. So this side is again 0. And we have again the sufficiency condition. Any question? Raise your hand, please. So we have a proof of the sufficiency condition, which says this equal to 0 for any u. Any u. Well, there's a simple example. In that simple example, the Hamiltonian is linear, so it is certainly concave. It's a function of lambda only. And so it is certainly concave in x, because this is linear here. And so Hamiltonian, the control that we got in this problem, example 2.2.3, are optimal. Sufficiency condition satisfies. There are some remarks here. If terminal condition xt is not constrained, it's called a free endpoint problem. If it's a free endpoint problem, then what happens is that this quantity, because the free endpoint problem, this quantity may not be 0, but this is 0. This is not 0, but this is 0. But what happens if I give you a fixed endpoint problem? Fixed, that means I want xt to be exactly a number or a vector if it's a dimensional problem. So let's say in the single dimensional problem, it's number. Suppose it's 5. So I want xt to be exactly 5. But then optimal control would have the control so that the optimal trajectory of that control would also be 5 at the end. Which means that in the fixed endpoint problem, this quantity will be 0 because xt will be same as x star t. Because I cannot take any trajectory that doesn't give me other than 5. So this will be 5, this will be 5, this will be 0. If this is 0, then this doesn't have to be 0 for sufficiency condition to hold. So the maximum principle for a fixed endpoint problem will not say lambda t equal to sx. It will say lambda t is free. It can be anything. Because it can be anything. And even if it's anything, this product is still 0. So we don't need to constrain lambda t equal to Sx. Because Sx has no meaning anyway because x star t is fixed. So there's no way to take a derivative of something which is fixed. So this one doesn't even exist. Okay, so that's all that. So here's xt equal to k, and then you have this, but this is 0. So lambda t is beta, which is the vector to be determined, a vector of constant to be determined. If it's n equal to 1 single dimensional, then beta is a number to be determined. So what happens is, if you take the 2-point boundary value problem, yeah. So what happens is when for a free endpoint problem, I have initial value and a terminal value, and I solve the problem that way. If I have a fixed endpoint problem, then I have x0, but I also have xt. So I have two conditions on x. But if I have two conditions on x, then I cannot have any condition on lambda because there's no way I can have this set of differential equations with more than two conditions. With more than two conditions, that there won't be any solution. So this lambda t has to be free. So if there are two values of x that are fixed, then this lambda t, I make it free. So lambda t equal to beta to be determined. So I have two values of x, but neither lambda 0 nor lambda t. So again, it's a 2-point boundary value problem, but 2 points boundaries are on x and not on lambda. So now we go to a numerical example, and that's when we finish. And you have a homework to do that. And it is the numerical example uses Excel. It can only solve simple problems, but it gives you an idea of what is going on. Okay, here's our problem. So this problem is more complicated. I take 0 to 1, no s, is a free endpoint problem because there is no constraint on xt. So I have x dot equal to this, x0 equal to 5. I apply the maximum principle, so I take the Hamiltonian. Lambda dot is given by this, lambda 1 equal to 0. But notice I cannot solve this equation unless I know x. And I cannot solve x equation unless I know lambda. And so I have two equations in x and lambda. I have x0 equal to 5, lambda 1 equal to 0. I have 2-point boundary value problem. So this is a system of equation I solve like this. So I guess the value of lambda 0. When I guess the value of lambda 0, I can solve these in a forward setting. So x0 and a lambda 0, I can solve these two equations by theory of differential equations. I solve the system forward in time. When I solve the system, I will find what the value of lambda 1 will be in that system. So I'm going to ask, is lambda 1 0 or not? If it is yes, I stop. If it's no, I take another guess of lambda 0. I keep going until I stop. I keep guessing. So one way is to guess brute force, keep guessing until you get there. One way is to have some kind of a method to guess. And that's where whole computational optimal control theory goes into. It goes into how to compute these things, how to make these things more efficient. I don't go there anymore because I don't have any chapter on computations anymore. So our computation will be limited to Excel. If you do more than that, if the problem cannot be solved by Excel, you have to go through computational papers or books to solve your problem if you need that problem in your research. How do we do that? How do we solve Excel? Well, Excel we do discrete time. First, we have to discretize the problem. So I discretize by delta. So the substitution of delta x delta t for x dot and delta lambda delta t for lambda dot gives me these equations. So these equations are directly derived from these two equations. So I can derive these equations directly. So you see x dot x plus delta t minus xt divided by that delta t is x dot. So for x dot, this minus that divided by delta t is x dot. And on the other side, it is that. So that delta t moves onto this side, and I have an equation in discrete interval of delta t. Same thing for lambda. I'm going to have to give some value delta t, which is 0.01, let's say. And I have to give a guess lambda 0, some guess. I give you some guess, and I have x0 equal to 5. Once I have this, I can solve this problem very easily. Numerically, it's very easy to solve because I put the value x0 and lambda 0, which is given. Then once I have the value x0, lambda 0, I put those values, I multiply that by 0.01, I get these values at delta t. So I have x of delta t, lambda of delta t. Once I have x of delta t, lambda delta t, I change this to 2 delta t, then I put the value of x delta t on this side, multiply by delta t, I get the value of x2 delta t. I keep going until I get to xt, which is x1. So you can see how I solve the differential equation discretely. It's easy. It's just go one step by one. Okay. Again, that's a bootstrapping, right? You begin with delta t, then to delta t, then to 3 delta t. I keep going until I get to 1. So this is hard to see. I cannot, oh, yeah, I can increase a little bit. So you can see that you put these values in column 1 and column 2. And as soon as you give the guess of this value in these two columns, this is 1 and this is minus, this is lambda column, this is x column. So you put the equation in x1 column and lambda 1 column, and then you put the initial value. Immediately it gives you a trajectory. And the trajectory goes all the way to 100, all the way to 100, and 101, I suppose, because you begin with 1. And if you interval 0.01, you divide 1 by 0.01, you get 100 intervals, and you begin with 1, then you have 101 as the last point. So it gives you the trajectory in the sense it solves the differential equation. When it solves the differential equation, it finds the value of lambda 1. Okay? But lambda 1 is not 1 anymore. So what you do is you can say to goal seek, it says goal seek so that the value in cell A1001, which remember A is a lambda and a B is an X. So you can say A101, which is the lambda, which is the last number in this column. You set that to 0 because lambda is 0. Right now it is not 0. Whatever it is, I don't know what it is. I cannot see it, but it is 0. So you set that to 0, and then you put OK, and immediately Excel will go through all the guesses of lambda 0 and will give you that guess that will give that cell exactly at 0. So you get a new trajectory by doing that, and the new trajectory will have a 0 at 101 cell, and you can have a chart, and you chart it, so it'll give you the x and the lambda trajectories in the chart, and so you can see the lambda trajectory is going. Eventually, this is the x trajectory. This is the optimal trajectory x, and the lambda trajectory actually goes to 0, and the guess, whatever the guess is, it will make that guess. Okay, so that Excel does that for you. So that's, now let me see what I have in the book here. And we are pretty close to finishing the chapter. I will spend 2 minutes for you to ask questions. So, yeah, so you enter, I mean, the book has, these are not readable, but book has, tells you what to do. Kushali, I think given the way we do webinar,
Yes, Professor.
on the page 59 in the book, you have this called enter minus 0, cell 1, enter do, and then set cell. You can actually have a slide for that in between.
Okay.
Yeah, you can do Excel better than I can anyway. So you can figure out how to make it easier for you to for us to do this online.
Okay.
So I have one or two extra slides because I usually go on the board, but right now this is not easy to go on board. So just put the slides, those two slides, and then we are done. Otherwise, it's difficult to see these things here. You see?
Right.
Yeah. So those are the slides. Any question, guys, um, for the chapter right now? Because this is a very important chapter that you understand the theory, at least two proofs. There are not going to be many proofs. We will be solving the problem by applying the maximum principle. We're going to apply the maximum principle like a recipe. So what we're going to do now is you learn some recipe, and then you get a problem, and you look at your cookbook, you apply the recipe, and you solve the problem. Chapter 3, we will introduce constraints, and we'll give you a new recipe. But we will not give you the proof of new recipe. We'll give you some idea of why the new recipe is a good recipe. And then in chapter 4, we will put state constraint, and that problem makes it even more difficult. And we'll give you two recipes, two kind of formulation, a direct and indirect formulation. And we will, most of the time, the book uses indirect formulation, but the sufficiency condition will be in terms of direct formulation. And there's a mapping between direct and indirect formulation, so you can go from one to the other. But all the chapters after 4, the book goes to indirect formulation. Okay, so we will go through that in chapter 4. That chapter 4, by the way, is the most difficult chapter in the book, and it is just to do a justice to it requires a lot more high-level mathematics. And I have a survey of state constraint problem in Siam review. So if you want more of that, then the survey is listed as Sethi, Hartle, and Vixen. I don't know where it is, but I will give you in a second. No, Hartle, Sethi, and Vixen. I'm sorry. It's alphabetical.
Professor, are you looking for the one? I think it's on page 135.
Oh, 135. When I was looking at the reference at the back of the page, which is 500, and oh yeah, it is here. How come survey is not listed at the end of the book? Oh yeah, here it is. Oh, this is not correct. Kushali,
Yes, Professor.
go to page 503 of the book. I'm my paper Hartle Safety Vixen is at the second from the bottom. Right?
Right.
But alphabetically, Hartle code should be before that. K comes before S.
Right.
Somebody goofed up the alphabetical order on this. So the court, Novak, court, all of these have to come before Hartle Safety Vixen. So the reference Hartle Safety Vixen has to move from 503 to 504. Another correction on the edit.
Okay. I thought they went by years though.
Huh?
I thought they went by years. the year it is published.
No, 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 it's not by year. It is by year? No. Yeah? No. No, 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 no. That's not by year. It cannot be by year.
Okay.
No, no. Look at the top two. Hartel Luptachik after Melman, right?
Right.
It's not by year, right?
Right.
So somehow it did not get alphabetized. I don't know how that happened. Who did the alphabetization? I do not know. You need to. There's a software in the LaTeX that gives you that alphabetization. So I don't know whether this is the only problem or there are other problems. I really don't know that.
Okay. We can talk about that later.
Yeah. Yeah. Okay. So yeah, thank you. That is the survey, which is more on a state constraint problem, but I see many papers continuing to come. I just saw 2 days ago somebody cited that survey. And so what I'm trying to say is that the state constraint chapter 4 is still developing. The theory is still developing. So I keep changing it a little bit, but at some point I cannot change anymore because the new development is mathematically much more challenging. And so I basically just leave it there. So what we have chapter 4 right now is more or less what it will be in another 2 editions. It will not go change much. So you have to basically go to, if you really have the problem and if you really need something more, then you have to go to the literature to do something. Okay. Thank you very much. And we'll see you next Thursday.
Oh, before you leave, I need to assign the homework.
Please
So
do
if you
that.
want to write it down, I'll also email you. The problems are 2.22, 2.30, and 3.31. Again, it's 2.22, 2.30, and 3.31. They're due by next Thursday, February 4th by 12:45 p.m.
Let me just a second. Yeah, 2.30 is exactly asking you to solve that problem by Excel. So you have to turn in the Excel solution somehow to Ming Ming. Okay?
Sorry, Kushali, could you repeat the questions? Sorry for that.
2.22, 2.30, and 3.31.
Okay, got it. Thank you.
You're welcome.
Please read chapter 3 because it moves very fast. We don't have any proof in chapter 3. But so it's a lot of recipe and a lot of maximum principles, one thing or another. So it goes rather fast, but there are a lot of notation and everything. So in order for you to absorb that in the class and be able to ask questions that you don't understand while reading it, that's a better use of your time as well. So please do that. Okay, thank you. Bye now. Take care.
Thank you, Professor. Goodbye.
Thank
Yeah.
you.
Thank you, Professor.
Bye bye.
Thank you, Professor.
Thank
Bye.
you. Bye bye.